Yes, I start recording. And hello, everyone. Welcome to our seminar today. And today's speaker is Satar Vakili, who is a researcher from MediaTek Research. And he will present our work, improve convergence rates for sparse approximation methods in kernel-based learning. So Satar, could you share this topic if you can?
Sure. Hi, everyone. This is Sattar. I'm going to present this paper, Improved Convergence Rate for Sparse Approximation Methods in Kernel-Based Learning. This is a work from MediaTek Research in collaboration with Jonathan Scarlett from National University of Singapore. This was presented at ICML this year as a spotlight presentation. So feel free to ask questions. Okay. Kernel-based regression is a very popular technique in practice to extend linear models to very general nonlinear ones. And it has a vast application in different fields, from parameter tuning in neural networks and machine learning in general, molecular design, recommendation systems, sensor networks. So the general idea is that they provided a data set from a nonlinear functions. We can derive closed form prediction and uncertainty estimates for this function. And one interpretation of this prediction and uncertainty is the posterior mean or maximum likelihood estimate of the Gaussian process model. And the interpretation of the uncertainty is the posterior covariance of a Gaussian process model provided this data. So regarding the notation, this mu n is the posterior mean or basically the prediction of the Gaussian process model, the maximum likelihood estimate. This Kn is the posterior covariance after n observations. This Kxn is the covariance matrix or the kernel matrix, which is the pairwise value of the kernel between these 2 points. And Kxn dot is the kernel between the observations and the point of interest. Yn is the value of observation. These are general formulas, but the important thing is that we have closed form expressions based on data for these two quantities, prediction and uncertainty. One drawback of this very nice and powerful modeling tool is the high computational complexity that goes with order of n cubed due to this matrix inversion step that is involved here. So to just like intuitively see what's happening here is that, let's say I have an unknown function and I collect one observation point, the red cross point from this function. And based on this observation point, I can create a prediction, which is this dotted black line, and an uncertainty region. So basically, plus minus a factor of the standard deviation that says the unknown function will, with high probability, be in this region. So, and I can just collect more points and create a better and better prediction and narrower uncertainty region for the function. And this is a very powerful method which allows me to, using a relatively small number of observation points, create very powerful representation for a nonlinear function. Just a quick note, because this will appear later in the talk, that there are two interpretations for what we did in these slides. So one is the Bayesian interpretation that assumes there's a Gaussian process prior for the unknown function. And then the prediction is the posterior mean or maximum likelihood estimate, basically the expected value of F condition on the data. There is an alternative interpretation that uses a reproducing kernel Hilbert space concept, which is a certain Hilbert space over the functions, and says that the prediction, this prediction is the arg mean of this expression. So the prediction is the least square estimator of the observations in a regularized way, where the regularization is with the norm of the RHS, with the norm of that space. So just like two different interpretations of the formulas that we saw for prediction. We can either see it as a Bayesian model where we have a prior on F and we use the data to do a maximum likelihood estimate, or we can say F is unknown in a certain space. Let's find a regularized least square estimate based on that level. And it can be proven that these two interpretations give us the same prediction. Okay, so this is we arrive at the kind of topic of this paper or topic of this talk. So we saw that a kernel-based model, either interpretation that we like, Bayesian or frequentist, give us very powerful representations for non-linear functions in certain spaces. But the drawback was that the computational complexity was order of n cube. So that's the main drawback for these methods. And so there are certain methods, certain ways, which are basically a sparse approximations of the inverse matrix to reduce the computational complexity from order of n cube to order of n. So we want to first quickly review this method, see how it happened, and then the contribution of this work is to quantify the quality of such approximations. So we want to discuss how good these approximations are and the predictions that they provide, basically how good they are. We studied this both under a regression model where we want to regress an unknown nonlinear function, and also under optimization, in an optimization problem, like a Bayesian optimization problem where there's an unknown nonlinear function and we want to optimize it. So we want to see the quality of this sparse approximation. So these formulas are, yeah, a bit scary and big. I don't expect anyone who is not familiar with this to try to grasp these formulas in one look. But the general idea is, rather than using the inverse of covariance matrix, we introduce a small set of inducing points. So previously we had xn, which was the set of input of the data points. Now we introduce a small set of inducing points zm, and we use this zm to describe the prediction and uncertainty. And what happens is, rather than inverse of n by n matrix, which we had previously, now we have the inverse of this m by m matrix. So basically this kzm here is the covariance matrix just between zm, the points in the set of inducing points, and kxnzm is the pairwise covariance between the data points and zm. But the important thing is the matrix that we're inverting is an m by m matrix, so that gives us this order of m cube complexity rather than n cube. And there's an additional nm squared, which if m is sufficiently small, then it's basically order of n, which is a significant improvement in the computational complexity of kernel models. So without really aiming at memorizing or grasping what these formulas are, I will try again to intuitively just explain a bit this approximate prediction and approximate uncertainty estimate.
I have a question about using the word sparsity, because usually, for example, when you talk about a sparse matrix, it means that it's a matrix with a lot of zeros in it.
Mm-hmm.
While here, instead, it seems very different, because we are just designing a new data set that is smaller. What's it called, sparse?
So I think it may come from the practical way of implementing these things. So in practice, ZM is usually chosen as a subset of data.
Okay, so it's like you're basically setting a lot of data to zero.
Exactly. So it's in this K transpose X and ZM, K, X and ZM. The transpose of this, if you can multiply like K, X and ZM with K transpose X and ZM, that's like a sparse matrix where we have set some rows to zero.
I see.
But theoretically, ZM doesn't need to be a subset of data. It's just like any set of a smaller number of them. But so these methods are referred to as sparse variational Gaussian processes, or Nyström method, which basically are the same thing almost, and they refer to the Bayesian and frequentist interpretation of kernel-based learning. So now let's see, basically based on each one of these interpretations, what is the meaning of the formulas that we saw in the previous page. So from a regularized least square estimator for regression using a kernel, the idea is that rather than choosing our estimator from the RKHS corresponding to the kernel K, we choose our estimator from a smaller RKHS corresponding to a kernel Q, where Q is defined as this using the set of inducing points, using the set of M inducing points. So basically, we define a different kernel, which is the span of these M points. So the RKHS corresponding to this kernel is the span of these M points in certain space, rather than the full kernel. And the prediction is basically the regressor in the least square estimator, regularized least square estimator within this smaller space HQ rather than HK. From a Bayesian perspective, what happens, this is a variational model. So basically these M points introduce a parameterized GPU family, parameterized family of Gaussian processes, and using evidence lower bound or elbow, we basically just find the best distribution in this family that approximates the true distribution. So it's like minimizing the KL divergence between the true distribution and an approximate distribution parameterized using this set of M inducing points. Okay, I cannot go back apparently. I can just go forward. Okay, that's good. We will never come back in this presentation.
Sure.
Okay, so this is the main result that we have. One of the main results in the paper. So we proved that the approximate posterior variance. So let me see if I can go back. Yeah. So we saw that this like approximate prediction, approximate posterior covariance using order of n computation rather than order of n cubed. And we saw like what is the interpretation of these formulas. Now we want to say how good these approximations are. So this is the aim of this paper. So somewhat surprisingly, there's not much work on how good these approximations are, although they are widely used in practice. So we proved that the posterior variance, the approximate posterior variance that we saw in the previous slide, can be decomposed to 3 terms. So the first term captures the maximum prediction. The first term captures the projection error from the bigger RHS to the smaller RHS. So basically, if F tilde is the projection of F into the smaller RHS, what is the error in this projection? The second term captures the prediction error from noise-free observations within the smaller RHS. So assume like our data didn't have any noise. So this captures the prediction error from noise-free observations. And the third term captures the effect of noise on prediction error, basically the power of noise in the prediction. So basically our theorem is a decomposition of the posterior variance into 3 terms. The projection error, prediction error from noise-free observations, and the effect of noise, which is a very useful theoretical tool. So basically, this is a very useful theoretical tool that leads us to some other important results. But before moving to that, so this is general. So this theorem is generally true for the formulas that are very popular in practice and we saw in the previous slides. But a good prediction needs a good set of inducing forms. So these are 2 separate things. So that theorem is always true. But if we want the prediction to be good, we need a good set of inducing forms. So that theorem holds for any set of inducing points. But for mu tilde to be a good approximation of F, the set of inducing points should be selected efficiently. So we observe that the effect of inducing points in the error is concisely captured in the spectral norm of the error matrix, of the error in the kernel matrix. So basically, we had one kernel K, which was the original kernel, and one kernel Q, which we defined using the inducing points. So if the spectral norm or maximum eigenvalue of this matrix is controlled, then we can control the error in approximation. So this is an interesting observation from our results, that if lambda max is the maximum eigenvalue of this error in the kernel matrix, then we can use this to bound the prediction error. And this is basically our theorem. So our theorem captures the confidence interval. So let me just maybe go back to one of those figures in the earlier slides, so it makes more sense. So this is what we're trying to capture here. So I want to find these confidence intervals where the true function value remains basically in this confidence interval with hyperbole. So this is the aim of this theorem. So the theorem is capturing the how wide this confidence interval should be, so that with high probability we can say that the function is there. So basically, the difference between f, the true function, and prediction, which is the sparse approximate prediction rather than the true prediction, is upper bounded by a factor of the standard deviation, which is again a sparse approximate standard deviation of the true standard. So basically what this theorem is saying is rather than true mean and true standard deviation, we can use a sparse approximate mean and a sparse approximate standard deviation. And the confidence interval still holds true with a confidence interval that's multiplied beta delta, which only, so in comparison to the true confidence interval, only scales with lambda max, with the maximum eigenvalue of the error in the kernel matrix. So the rest, the other terms are standard terms in kernel-based learning. So basically the second term is something very similar to Chernoff-Hofting inequalities. And the first term, the CK, is the RHS norm of F. there's an upper bound on the RHS norm of F. So basically, the norm of F higher, the confidence interval becomes larger. But we show that the effect of basically this sparse approximation is kind of very precisely captured using this lambda max. So this is the contribution of this theorem. This confidence interval holds true only for a fixed x. But if the domain is finite, so if there are only finite number of x in the domain, we can extend this to uniform confidence intervals with a probability union bound. We only need to replace delta with delta divided by the size of the x. If the domain is continuous, more effort is required, and we need to use a discretization argument to extend this confidence interval to uniform confidence intervals over the entire domain. You see the difference, right? So basically the difference is this. So this is my true function, and this is my GP prediction confidence interval. So this is the question, like, is the confidence interval true only for one point, or is the confidence interval uniformly true for all points? So to extend from one point to every point, we need to use a probability union bound. And if the domain is continuous, we need to use a discretization argument. But anyway, we show that the confidence intervals more or less hold for continuous domains uniformly. So again, like with high probability, with probability 1 minus delta, the true function and the sparse approximate predictions are within like a constant factor of the standard deviation plus minus terms which go to 0 at order 1 over square root and roughly.
I have a question about this. So the union bound is a rather loose way of answering the question of what is the error across the entire domain. Because if I remember correctly, it basically assumes that there's some assumption of independency of different points, right? So it's kind of the worst case scenario. I mean, in practice, there are going to be correlations between the error that you make at one point and the error that you make at another point. They're not going to be dependent, right? So somehow, if you take this account, if you take into account these correlations, you should be able to get a much better bound. And if you have, if you know, for example, how these correlations change continuously, if you have a continuous space, then you should be able to draw some much better to be able to have better results, right?
Yeah, that's a very good point, actually. That's a very nice point. So if you look at these two terms, we pretty much reserve that for the extension. So for this beta delta, we pretty much like preserve what we had for without like extension. So I think, so my point is, yeah, I think you're right. There should be an improvement if we do it in a more smart way. But the improvement only perhaps results in the constants.
Yeah, I agree. Yes, only in the constants. Yeah, it wouldn't change the scaling. Yeah, that's true.
And I think the reason is that the number of points only appears inside the log term. So basically, although there are like so many points, it just like logarithmically affects the confidence interval. I hope this is clear. And again, yeah, there's like so much mathematical details. I don't expect someone to remember or understand these at one look, but I just thought to keep these here, just show what is involved, basically. So basically, we have this sparse approximate prediction, sparse approximate standard deviation. The only thing is this confidence interval that which we want to mathematically prove that is valid. And this is very similar to the confidence interval that we had for the single point at a fixed point. And again, like kind of like the crucial thing is this lambda max, or the maximum eigenvalue of the error.
So, I mean, I'll answer a very simple question of the practitioner. What you're saying is that when I use an SVGP, and if I just use the prediction, so the uncertainty bounds that SVGP gives me, it will be overconfident, right?
Mm-hmm.
So if I just use the, mu tilde and sigma tilde, which is just what I get from the SVGP, so those bounds are overconfident. Is that correct?
I don't understand what you mean by overconfident.
So I mean, by overconfident, I mean, will the true function actually lie between those bounds?
Yeah, but it kind of comes through this confidence interval-based multiplier, right?
No, I mean, so yes, so that's the true function. So you're saying your theorem states the true function is within this interval. I'm saying if I'm a practitioner, I'm just using plain SVGP, right? With the SVGP mu and the SVGP sigma. And if I say that, okay, if I have plus 3 sigma minus 3 sigma, I have this much confidence that my true value is within these bounds. Is that so? Am I being overconfident when I do?
I think so.
Okay. So is there a way, so can I use these factors to maybe correct for my overconfidence if I'm using an SVGP? Is it computationally efficient to compute these factors?
I see. I don't think the problem is computational. The problem is a bit more philosophical in the way that I think we look at the problem. So if we make the assumption that our prior is a GP, so I find this a bit philosophical. I'm not sure how others look at this, but I have a practical problem. I have a data set. I'm looking at this data set. I use a GP model, a SVGP model, I make a prediction. So if I make the assumption, because anyway, I am making this assumption. When I come up with these formulas, we are making the assumption that we have a GP model that we are finding is posterior mean and posterior variance. So if I make the assumption that the true underlying phenomenon in the real world is a GP, then plus minus 3 standard deviation is the 95% confidence interval, right? Okay, that's actually but then so I think it comes on the validity of that assumption. So this is under a different assumption. This is saying that that function f is a fixed function, an unknown function. So as long as its RHS norm is upper bounded by CK, this is true, right? So basically how we interpret these depends on the exact mathematical modeling assumption that we have for the problem. But when it comes to the practice, yeah, if I have a mean and if I have a standard deviation, I may go with plus minus 3 standard deviation, see what happens, right?
Hello, Satar.
Yes.
This is Pei Yuan. So in the previous slide, you mentioned about like the confidence interval for a single on a single point, right? And here you want to discuss about like a uniform bound over all x. I'm wondering, exactly. In doing so, do you assume some property of the space X you're considering? For instance, you assume that X is a compact set so that you can cover it with a finite subcover or so on? Or is it related to the covering number of this of the set X you are considering?
Yeah, sure. So basically, the assumption is that the X is compact. Basically, there's a closed, for example, subset of RD. But more important than that is that our underlying function f has some sort of like Lipschitz continuity. So when we use this discretization, what we find out also holds for the other points which are not in the discretization. So the assumption is basically has two most important things, like X is compact and F has some Lipschitz-like properties, which are not very restrictive assumptions, are like common and standard assumption, especially F is Lipschitz-like. Basically, the consequence of F is in RKHS for most kernels. So F is in RKHS for most kernels, for example, a squared exponential implies that F is Lipschitz-like with certain like parameters, which is sufficient for basically proving this theorem.
Okay, that makes more sense. Okay, thank you.
Thanks. Okay. So basically, we prove that this confidence intervals hold uniformly for all x. So about the inducing points, there has been like quite a lot of work in the literature. There are several ways of selecting this inducing point. One way is to draw them from XM. So as I said, in practice, like inducing points are usually just selected from the existing data. So one way is to just like draw them based on a certain distribution, which that distribution is KDPP. Another way, which is very popular in practice because it's very easy, is K-means clustering. And there's also like a literature on choosing the inducing points based on something called Ridge leverage score, which basically determines how important this data point is for a regression model. I'm not going to go into the details of this because it's like a kind of orthogonal research track to what we have. But basically, any of these methods which ensures that lambda max is bounded or that lambda max can be controlled, which is basically the maximum eigenvalue of kxn xn minus qxn xn, is sufficient for basically our theoretical results. So as I said, yeah, so basically what we want is lambda max to be controlled. So basically we use the results from this last paper, this paper, which basically says as long as the number of inducing points is as many as the effective dimension of the kernel, which is roughly speaking the same as maximum information gain. Again, like this is, I'm not going to go into too much of details of this. For people who are familiar with the kernel literature, this should make sense. But basically, we can, for any specific kernel, we can define an effective dimension or maximal information gain, which is kernel specific. Basically, by determining the kernel, that quantity will be determined. And as long as the number of inducing points is as large as the effective dimension, the results of the paper, that paper shows that the maximum eigenvalue of the error in the kernel matrix can be upper bounded by tau squared with high probability. So in our confidence interval, we have terms like lambda max divided by tau, square root of lambda max divided by tau, and that just turns to 1. So which shows we're not really losing much because of the approximation. But then we apply this to two well-known problems. So one is the convergence of mu tilde to f. So we have a function f, a regression function, and we have this observation points, and we have a prediction using this sparse approximation method mu tilde. And the question is how this mu tilde converges to f. And we have a theorem that we prove that mu tilde uniformly converges to f at a rate order of square root d is a fixed number, which is the dimension of the input, gamma k n divided by n, basically effective dimension divided by n. And this gamma k n effective dimension or maximal information gain is logarithmic for very smooth kernel like a squared exponential. And it's always sublinear, and basically this term decreases polynomially for family of Mattern kernels. So here I think we have it. So here I have the specification for these two popular kernels. So basically Mattern and squared exponential are perhaps the most common kernels in practice. And in the case of a squared exponential kernel, the result I showed in the previous page, which means was order of 1 over square root n, uniform convergence to f for mu tilde. For the Mattern kernel, it's a polynomial convergence slower than a square root 1 over square root n to f. In comparison to the existing work, this paper, Bert et al. 2019, they received ICML 2019 Best Paper Award, bounds the KL divergence between the approximate and the true distribution. Their bounds hold on expectation because they use the GP model and they assume F is a GP, so the bounds hold on expectation. This more recent paper, 2021 paper, proves similar bonds on the KL divergence between the true and approximate distribution when F is a fixed function. They also have similar results to our theorem on the convergence. In comparison, this 2021 paper require number of inducing points similar to ours, while Bert et al. Paper require a much larger number of inducing points. It may not be a fair comparison because what they prove is stronger. So what we are proving, we're proving that the approximate prediction converges to F. What they are proving is that they're proving that the KL divergence goes to 0 between the two distributions. So the latter is a stronger result. So proving that the KL divergence goes to 0 is stronger than proving that the means converge to each other. We're not actually only proving the means converging to each other, we're proving mu tilde is converging to F. But because of that, we get a stronger result on the number of inducing points, which we basically prove with a much smaller number of inducing points. And mu tilde converges to F. So in comparison to Niemann et al., we have a completely different proof technique. We use the decomposition of the posterior variance while they use similar techniques as Bert et al. And in addition to this, we also consider optimization problem, which doesn't exist in the previous papers. The optimization problem may be a bit more tricky because in the regression problems, we usually assume that the observation points are selected a priori or in an offline way. So there is no skewness in the posterior distribution. While in optimization, we choose these points sequentially, which adds like additional complexities to the confidence intervals and the regression results. So this is the optimization problem that we're considering. So there's the nonlinear function f. There is an optimum point, let's say the maximum point for this function x star. And we want to select a sequence of points like x1, x2, x3, x4, and so on, so that they converge to this optimum point. The performance is measured typically in terms of regret. That is the cumulative loss in the value of f at the observation points x1, x2, so on, compared to the optimum point. So what we do is we use an adaptation of batch exploration algorithm, which is this paper is published in AStats 2022. Sorry, I haven't updated reference. By replacing the exact GPS statistic with approximate. So basically, we take an algorithm for the classic Bayesian optimization, and then we just replace their exact GPS statistic, exact mean and standard deviation with the approximate ones, and we basically provide a analysis of this approximate algorithm. So this algorithm proceeds in batches of observation. During each batch, the points are chosen with the highest uncertainty, and at the end of the batch, the points which are unlikely to be the maximizer are removed using the confidence intervals. So here, the importance of having these confidence intervals in analysis of this algorithm. So I'm not going to basically spend much time on this algorithm and how it works, but basically there are several rounds. During each round, the points are chosen based on maximum posterior uncertainty, approximate uncertainty. And at the end of the round, the points are tuned by removing the ones which are unlikely to be the optimal. And for this second part, we use the confidence interval. So for this algorithm, we show that with high probability, the regret is in order of square root n, this information gain of n. And because information gain is sublinear, this regret bound is always sublinear. In fact, this is order optimum. We can specialize it for a squared exponential and Matern kernel again using the bounds on the information gain. And this has been proven to be the best achievable regret bound in these cases. So basically, we prove order optimal regret bound for an algorithm which uses a sparse approximate GPS statistics. So that means order optimal regret bound algorithm with a state-of-the-art computational complexity. Excuse me for this problem. So another work to compare with this is 2019 ICML paper, where they proved order of gamma k and square root and regret bound for upper confidence bound based UCB-like algorithm. This is, however, not optimum in comparison to our results. This gamma kn is outside the square root rather than being inside. And the regret bound, basically this regret bound fails to be sublinear or it becomes trivial in many cases of interest where this gamma kn grows faster than a square root n. So basically our algorithm can be seen as the first order optimum regret algorithm with a state-of-the-art computational complexity. That's it. So to summarize, so basically, so the kernel-based regression and it's a sparse approximation. So this SVGP or Nyström method. So our main result is like a novel formulation of a sparse approximate variance in terms of projection error, prediction error from noise-free observation, and the effect of noise on the error. So this helps us to establish novel confidence intervals for the sparse approximation method. And we can basically use this result to prove as corollaries novel results on regression and also improved regret bounds for optimization problems using a sparse approximation method. Yeah, that's it. Thanks a lot. I will share this slides later with the organizers to share. There's like a list of references if someone is interested. Yeah, if you have any questions, I'll be happy to take now.
So the Bird paper got